Today we're going to learn about the calculus of vector functions. To begin, let's talk about what the derivative of a vector function is. To begin this illustration, let's look at a curve that represents a vector function in the xy plane. Suppose the curve looks something like this, representing an arbitrary vector function. Being a vector function, this curve has an orientation indicated by the direction of increasing values of t. Let's start off by looking at a point on this curve. We will call this point P. Point P has a position vector that represents its orientation or its location relative to the origin. We will label this position vector r of t, where t is the parameter for this vector function. Now this point P has an x component with a value of x of t, and a y component with a value of y of t. Let's now look at a second point on this curve. The second point we will label Q. Point Q also has a position vector, and we will call this position vector R. And because this takes place at a later point on the curve, we're going to say that this takes place when there is a small interval of time, delta t, that passes. That means point Q, its x component would be given by x of t plus that small interval of time, delta t, and its y component is given by y of t plus delta t. We could construct a vector between these 2 points, between points P and Q. Here is our vector there. Let's label this vector PQ. And PQ is defined to be the change of our position vector. Well, this change in our position vector is our position vector at t plus delta t. So that's point Q minus the position vector of point P. Let's now look at what happens when we allow the change in the parameter to get smaller and smaller. So in other words, as we allow delta t goes to 0. So what will happen is point Q will get closer to point P. As delta t gets smaller and smaller, point Q gets closer and closer to point P. The vector PQ is defined as the change of position between points Q and P. And that's just given as the position vector at point Q minus the position vector at point P. But you might have noticed that as our parameter approaches 0, and that's represented by Q getting closer and closer to P, our change of position approaches 0 as well. So in other words, Q and P are getting closer and closer together, eventually becoming indistinguishable. Well, if you look at this, that if t goes all the way to 0, then we could say that our difference in r approaches a differential in r as our parameter interval t approaches our dt differential. Well, think about it like this, is as we look back at this animation, notice how if delta t changes at a certain rate, this can be considered almost like a derivative, a rate of change as one point approaches or recedes away from another point. So we could see that the position function changes at a certain rate, delta r. Well, let's look at that rate relative to the parameter t. Let's just call that a velocity. Velocity from our physics courses is the rate of change of position. So let's call the velocity of our curve, and in this situation, we will call it the average velocity of our curve. We will define it to be the displacement between points P and Q over the time interval in which that displacement takes place. If we look at the limit as delta t, our change in our parameter approaches 0, of this average velocity of our curve, that is just the limit as delta t goes to 0 of our displacement over delta t. Now, this is cool, because this now is just our definition for the velocity of a curve. We have now just defined the derivative of a vector function. The derivative of a vector function is defined to be the limit as the change in the parameter goes to 0 of our average velocity of our curve, which is just delta r over delta t. This should look very familiar because this looks a lot like a derivative when we just had a function of a single independent variable. Except this being a vector function, this is a derivative over the components of a vector. Let's take a look at that. The derivative of a vector function is found by just taking the derivative of the components of that vector function. So a vector function has components that are functions. In the rectangular coordinate system, that would be an x component, a y component, or a z component. Or more generally, if we don't want to restrict ourselves to the rectangular coordinate system, we could just say some function f that's a function of t, g that's a function of t, and h as a function of t. This derivative distributes into each of the components. So the x component becomes the derivative of x with respect to the parameter t. The y component becomes the derivative of y with respect to t. And the z component becomes the derivative of z with respect to t. Now, you might remember from beginning calculus that the derivative of position with respect to time is called velocity. So the derivative of x with respect to time is velocity in the x direction. I'll indicate that with a subscript 1 for the velocity in the x direction. The velocity in the y direction will be v sub 2. The velocity in the z direction is v sub 3. And this is now the velocity of our vector function. And all that is, when I say velocity, that's just another way of saying the derivative of our vector function with respect to time, where we are differentiating each component with respect to time.